Hello everybody. Today we begin our subtopic based algorithm design lecture, and we start with our first lecture on the divide and conquer method. Till now we have seen that our approach of designing algorithms through initial solutions, their analysis, solution refinement and cause of development of data structures to form the final algorithm, and we have seen several case studies. Based on those case studies, we have started identifying how we will solve these equations and definitions. And our approach, just to reiterate, was based on development of an initial solution and looking at a recursive definition, an inductive proof of correctness, analysis of the recurrence relations to get the time complexity. Then we opened up the recursion tree, looked at the structures formed and the recomposition properties, and based on the choice of the solution, which was the core of the balancing the split and choosing an appropriate mechanism to split the problem, was the core of one of our approaches, and this is what we shall discuss in more details today as the divide and conquer method. Though this whole recursive definition itself is a divide and conquer approach, but in the terminology of algorithm design, this sort of methods have got a special place, and we shall look at them in more details now. We have also seen the other methods like identical subproblems, which leads to what is called the dynamic programming method, and then the data structure formation. We have also seen how pruning occurs in the search through the branch and bound methods, and we shall do all of them step by step. But today we shall discuss in more details the divide and conquer approach. So in order to understand the divide and conquer approach, let us understand how our recursive definition structure looks like. Our recursive definition structure, our function is fx. In order to solve this fx, we have what is called a base condition. And this base condition, let us say, is denoted by a Boolean function bx. And therefore, based on this base condition, we write our code as that if bx, then we return the result of the base condition, and let us say that the result of the base condition is a function jx. So this is our base condition. So this is our first step. Our second step in our recursive definition is called decompose, or is called the decomposition phase. And in this decomposition phase, we define a function dx, or the decomposition function dx. What it does is, it applies to x, and based on x, it returns something x1, x2, xk. It decomposes x into k parts. Now, how it decomposes x into k parts varies from problem to problem. We have seen some special cases like the split case. The third step in our method is recursive call. So what we do is, for each I, we compute yi is equal to f of xi. So we recursively call this recursive function on each of these decomposed subcomponents. Finally, we have what is called the recomposition phase. So we have a recomposition function Ry which recomposes each of the y's and returns some solution j. So it's a recomposition which takes each of the yi's, y1, y2 up to yk, and returns j, and finally it is the return, meaning the result, which says return j. These are our basic steps. So we have the base condition, we have the decomposition function, we have a recursive call, then we have a recomposition function, and based on whatever happens here, we get back our solution. To draw it pictorially, let us say we have our original call at this root, and then it recursively decomposes into several solutions, and then again it is decomposed into several solutions. Let us, for the sake of generality, assume that this one is a base condition and this one is a base condition. Then this is again decomposed, and there are many such in between which I am not drawing. So there will be many such decompositions. Let us say that this is decomposed, and let us assume that these are all base conditions. Now the recomposition starts. So these two are recomposed. This is how the recursion structure proceeds. These two are recomposed. This is not 2, actually this is a full set. I am sorry for saying 2, but it is not 2. It is a set which is recomposed. Then when these are recomposed, this is recomposed, and the final solution is obtained. So we have these circular functions as the decomposition functions. So this is where the functions are all decomposed into parts. So this is the decomposition function. So this is the decomposition function. Here we have the decomposition, here we have the decomposition. So these are all the decomposition functions, and with every decomposition you have a recursive call. So this is f, this is f, this is f, this is f, here is a decomposition, this is f, and this is another decomposition. And at each of these points the B condition holds. Wherever the base condition is true, we have the B condition holding, and when the B condition holds, then at every point in the B condition, what we have returning from here, in each of these B conditions, the J values are returned. From each of these B conditions, the J values are returned. And at the right boxes here, we have the recomposition happening. Now in terms of the costs that are incurred, we have now costs. There are costs for base evaluation, there are costs for decomposition, and there are costs for recomposition. And the total cost is the sum of all these costs that occur, and these costs depend on the size of the problem and the structure of the problem. Here x, as we just said, x is just the complete input. It may be a list, it may be a set, it may be a structure, it may be a lot of information. So the total cost is the cost of all these things. The next important thing to consider here is the evaluation. The evaluation also depends on the properties of R especially and D. It depends on the properties of the decomposition and the recomposition functions. For example, the recomposition function could be a simple max or a min, and these functions are both associative and commutative. So how would you use those properties to do that? So it is the structure of this recursive definition which really gives us our methodology and approach, and it is here that we start deciding on how we will go ahead with the next steps. Along with these costs and these recursive definitions comes two things which come associated with this. One is the proof. One is the proof of correctness. Which comes by the inductive definition of recursive definitions. The other is the cost, which is the sum of all these costs, but this cost also comes from the recurrence equation of time complexity. So this forms the basics of the recursive definition structure. Let us see some examples. We have done several examples before. Our first example was the max function. And if you know that in the max function, the base condition was for L equal to 1. And the decomposition function was a split of L. So if we had max L. And the recomposition function was, because the split of L, the recursively it returned the max of the sub was max. Was the maximum of two elements. And we know that from this, the cost of the split, so let us look at the cost. The costs of B was 1. And we are looking at only orders of complexity, so we look at it as order 1. The cost of D, the split, depends on how we store L. If L is an array, then obviously it will be a constant time split once you decide where to split it. On the other hand, if it is a linked list and you want to split it in the middle, then you would have to go. So this depends on how we store L and where we decide to split. And we knew that we have found in our previous analysis that every decomposition yields the same complexity, and therefore from there we are able to determine that we could do this split is also in constant time. And once we do this split in constant time, our recomposition function is the maximum of two elements, which is also constant time. And we also know that this function is associative and commutative. Therefore, because it is associative and commutative, this recursion tree, which is shown in this diagram, can actually be evaluated in any order. And this enables us to evaluate the recursion tree in any order, and as we shall see in more complex examples, it yields to some very, very interesting solutions. And based on this, we can solve the problems. We have also done other problems. We have done the Fibonacci problem. The Fibonacci problem, we know that the base condition is n equal to 0, n equal to 1. The split is n minus 1 and n minus 2. The recomposition function is the addition operator. And there are costs associated, and you can easily work it out. We have also done the coins problem. And in the coins problem, we again saw that our base operator was the null check, and whether L is equal to 0 or 1, and the decomposition operator was actually in one of the cases, where the first case where we chose one element at a time, in one case our decomposition operation was to move one element at a time from list T to S, if you remember the algorithm that we had followed. And based on the solutions that we got, our recompositions were finding again the minimum. In the other approach, for the alternative for the coins, a new decomposition function was found where we used the inclusion-exclusion principle. And each of these yielded identical subproblems. One did not yield identical subproblems, and so on and so forth. So looking at this, we come to the basics of the divide and conquer method. The important things to remember in the divide and conquer method is, one, is the mechanism of decomposition. And the choice points. Because we know that this decomposition function and the recomposition function develop our recurrence relation Tn, if we look at the way we had examined this structure of the decomposition into k components and then the recomposition, then if we are breaking it up into k components, then we will have this for the recursion, Then we will have the cost for decomposition of n plus the cost for recomposition of the k elements. Now these k elements could be a function of n. So based on this we will, so here we will have the various alternatives of D and R, and based on these various alternatives on D and R we will be able to decide on our method. In the current examples that we had seen, for both the variations of D and R, we had only seen our main choice points. In the examples that we had seen were on how to optimally split the problem. But as we will go ahead, we will see in this series of lectures of divide and conquer itself that the choice points may depend on various things that we have for D and R. The second thing about the divide and conquer method are related to the evaluation. The order in which we evaluate may sometimes become important. Which subproblems we evaluate first, whether we evaluate it in depth first manner, breadth first manner, and how do we evaluate it may also determine the way of the solution. Later on, in the other methods, the dynamic programming method will involve solving identical subproblems once and memoizing the past solutions. Then in our methodology will be the data structuring, or organizing data of past computation for future use. And finally, we shall see how the methods of branch and bound enable us for pruning of unnecessary paths in the computation of the recursion tree. And it is this recursion structure itself which yields new kinds of data structures. So with this we will also have various important aspects on, as we just mentioned, on the properties of of D and R. So the properties of D and R, associativity, commutativity, complexity, computation complexity, all of them will matter as to how we are going to solve that kinds of problems that we are interested in. So therefore, in this series of lectures on divide and conquer, we will concentrate ourselves on this aspect. We will concentrate ourselves on the choice points. How do we choose how to decompose and recompose? So our main aspect, so the main concentration of our effort in the divide and conquer is choice points. Choice of the D, which is the decomposition, and R, which is the recomposition. And from this decomposition and recomposition, we will get the time complexity. And we would like to optimize this time complexity. We will look at various options of choosing D and R for a particular problem and analyze the time complexity. And this analysis of time complexity comes in two ways. Analysis will come, one, by analysis of the recurrence equation, formed, and two, by analysis of the recursion tree and costs, here I mean computation costs, incurred during D and R. And we will have to make various kinds of choices to do that. Till now, our choice has mainly been on the split of D, which we got in the max problem, the max min problem, and the max second max problem. We also saw how we are going to split in the coins problem. The Fibonacci definition was already there. And the third is what structures are formed which enable us to develop alternative insights for an iterative solution to the recurrence, to the recursive definition. So these are the foundations of the divide and conquer method, and from these foundations of the divide and conquer method, we will now in this series of lectures, in these 2 lectures on the divide and 3 lectures on the divide and conquer method, look at various kinds of sorting and searching problems, as well as some other kinds of problems, which we shall discuss in the 3rd lecture on the divide and conquer method, where we shall talk about string operations, matrix operations, and things like that. So in the sorting and searching problems, we have various kinds of searching problems and various kinds of sorting problems. In the searching problems, we have searching of an unordered list. Which means that elements are unordered and we have to find an element. The second is ordered list. Ordered list or sequence. So we have an ordered list or sequence of elements, and we can be able to find this. The third is a combination. And there may be several variations. And the problem could be a static problem or a dynamic problem. A static problem is one where the list is or the input is all given and you have to solve it once. A dynamic problem is you have to solve it many times. And this dynamic problem, when you have to solve it many times, is a new aspect of creation of data structures. The sorting problem, again, is that we have to find the sorting of elements in some ascending or descending order, and among the sorting of elements, typically the algorithms look at in-memory sorting. That means the elements can all be stored in the memory for us to sort. Otherwise, it may also be secondary storage sorting when they are large, and they involve some more aspects of the sorting paradigm. Currently, we shall be concentrating on this in-memory sorting problem. In this current lecture, we shall look at the searching problem, and then in subsequent lectures, we shall look at the sorting problems. So the first problem that we look at is called sorting an unordered list. So that means searching an element in an unordered list. So let us call it search unordered list L, search for an element X. So we say let L is equal to S1, S2 up to Sn, and we have to look for an element X and say whether it is there in the list or not. So our base conditions, obviously, if L equal to 0, return false. If L equal to 1, then we have two cases. So if L was 0, we return false. If L equal to 1, we check if S1 is equal to X, return true, else return false. If this does not hold, then split L into non-empty L1, L2. This is our decomposition operator. Then we now call if search unordered L1x. If this is true, return true, else return search unordered L2, x. So this is the simple definition. These two form my base conditions. This forms my recursive condition, and this forms my recomposition condition. So this is my recomposition, this is my decomposition, and this is my base. Now this is such a simple problem that we don't have too much of a difficulty. We can easily check. It is not difficult to determine, number one, that the recursive definition will lead to our traditional costs, because we know that the cost of the split, if L1 and L2 are arrays, then the cost of the split is constant time, and the cost of the recomposition also is constant time. But we also know that the recomposition cost will call at least both of them, and because of the way both of them are called, and one of them, the final recomposition operator here, looking at this if statement, is actually an OR operator. The final recomposition operator here, this recomposition operator is basically an OR operator, and the decomposition operator is a split operator. Therefore, for our case, we know that this will be, we can break it up into more than one element, but we can also show that instead of breaking it up into 2, if we do 3 or 4, all of them will yield the same result. So we can show that if it will be tk, tn minus k plus order 1. And we have seen this recurrence before, and we know that whichever way we do it, the complexity will remain the same. And since we know whichever way we do it, the complexity will remain the same, and we have discussed this in the tournament data structures that are formed, our first solution to this is that the choice is any split is enough. Since instead of saying any split is enough, any split is equal in complexity to others. So to simplify everything that we do, we will choose one n minus 1, and we know that by this choice of 1 n minus 1, and this recurrence in any case evaluates to, n, order n, this evaluates to order n, we will choose 1 n minus 1, And once we have chosen 1 and minus 1, we know our split and everything else. So the solution, final solution of this can be done by an iterative loop for I equal to 1 to n. Do all we need to check if the list, if x is equal to Si, return true, and if it comes out of this, we return false. So this is a simple loop which we can do. The other thing, based on this choice, once we have made such a choice, we could have made any other choice. Once we have made this choice, we also analyze. So after having made this choice, so we have first thing in finalization is choice which we have made. The second thing is to check whether this is optimal. Now this part is not easy to prove for all difficult problems, but here it is easy to show that it is easy to show by a counter example that unless every element is checked in the worst case, we may not find the correct answer by any algorithm. That means no algorithm can guarantee to solve this problem without looking at all the elements in the worst case. However, it will depend on the exact question that is asked for us to be able to answer the question earlier or not. That means this problem can be solved because the recomposition is an OR function. It can be solved earlier. So, but there are variations. So let us look at a variant. The first variant is that we say search unordered LS, where you have, where we need have, so let us, we have L equal to L1, L2 up to Lk, which is unordered, and Ln and S is equal to S1, S2, Sm, both unordered, and we have to return the elements of S that are in L. So this two unordered elements, this is equivalent to which problem? This is equivalent to the problem of, so this is equivalent to the problem of finding, this is equivalent to the problem of finding L intersection S. However, we want to find out those elements which are common to both S and L. That is the problem. And how to solve this problem? How do we solve this problem? And we can have different variations. So I leave this solution to the finding of the intersection of two sets as an assignment, which you can do later. The next problem that we get is an ordered list, which means we have to find search ordered L X. Here we know that L is equal to S1, S2 up to Sn, but we also know that Si is less than equal to Sj for j greater than I. So this is our condition, which means that the list is ordered in ascending or non-decreasing order. The elements can be distinct, the elements can be different. So here we have a different strategy, because now we know that we could not only look at one element at a time, but we can now choose any one element in the list and split it in two parts, because once we look at L, so our approach, our decomposition function will be as follows. Choose, so this is our choice point, Si. And we decompose if Si equal to X, return true with value I. Otherwise, else we check if Si is less than X. So if Si is less than X, then obviously the list that has to be searched for, so we form L dashed is equal to Si plus 1 to Sn, and we return, we find Y X equal to search ordered L dashed X. And if Y is equal to true, if Y we will return value in the original, sorry, this cannot be X, so let this be Z, because we already know what is X. Z is the location where it is returned. Otherwise, if Y is true, then return Z plus I. That means we know that from I, Z more locations are there. If that is not true, we return false, and we can return any value, infinity, 0, it does not matter. Else, which is the else part of this, is that we will now form L dashed is equal to S1 to Si minus 1 And once we have formed this I minus 1, again recursively we will get y, z back. Will be search ordered L dash x, and the same thing if y. Now since it has started searching, because it was x was actually less than Si, because x which was less than Si, so we have to search on the right hand side. So we will return true, and we will return z, else return false and infinity or 0 or whatever. And in this part where we return z plus I, we also have to return true comma z plus I. So at this point we complete this portion, we complete the else part, and we have completed our algorithm. So our choice point here, our decomposition function, was again a choice of I, and based on this choice of I, we had to either look at we had to compare this element once, and we had to look at what was there, whether we move either terminate the algorithm or look left side or look at the right side. And what was our recomposition function? Our recomposition function again was an OR function. And here the OR function is necessarily computed only in one direction. Therefore, the time complexity from this recursion tree, the time complexity that comes out, Tn, is equal to, where we choose I, so it will be Ti either Ti minus 1 or Tn minus I plus 1, plus this one comparison that we had to do. So plus order 1, and out of these two, whether we move right or left, it will be the maximum. So it will be the maximum of Ti or Tn minus I. So how does this algorithm work? This is a very well defined algorithm. Let us just see how it works for a simple case. 7, 9, 12, 15, 18. Suppose these were my elements, and my x was equal to, say, 15. Then my choice in this, my choice could have been 9, and if I choose 9, then this will be split into 7 and 12, 15, 18, and because 9 is less than 15, the algorithm will move in this direction, and again I will choose, maybe my choice will be 18, and if my choice is 18, then this will split into 12 and 15, and this will split into null, and if it is null, there is nothing to do, the algorithm will return with failure. And then here again my choice could be 15, and once my choice is 15, the algorithm terminates with true, and since my algorithm terminates with true, the value that is returned from here is 2, true 2. And since the value returned from here is true 2, then the value that is returned from here, because this was at the second point, so it will be 2 plus 2, 4. So 4, true 4. Because 9 is at the second position, this is the first position, this is the second position, this is the third, this is the fourth, this is the fifth. So 9 here was the second position. Here again 18 was the third position. So because 18 was the third position here, so from here we will return 2, because the second position here 15 was the second position. So second 2 will be returned here, and since this was the left hand side, then again 2 will be returned from this side plus this 2 which was here. So this will return 4, because the choice point was 2, 2 plus 2, 4, and the fourth element is the actual choice. We could also have nothing returning. Looking at this, if we go back and we see what is here, then our base condition will also have to be written here. If L is equal to null, return with false infinity, which we had not written. We can come back and write the base condition here. And if we now come back and analyze it from a data structures view, then we will see that in the worst case, then the algorithm complexity, which we had seen was Tn is equal to max of Ti minus 1, comma Tn minus I plus 1 plus 1 or plus order 1. And if we look at the recursion tree, then it breaks up and the solution is found at the leaf nodes. So every leaf node is a possible place where the solution will be found, and wherever it is found, it is order 1 computation per node, and it goes down. So the complexity is the length of the tree, recursion tree in the worst case, the complexity being the length of the recursion tree in the worst case. It will be optimized. When will it be optimized? It will be optimized, this will be optimized if the worst case length is minimized. And the worst case length will be minimized, as we can see, if we split the tree into equal halves. That means if we split the tree equally, so the solution will be to split in middle. That means choose I equal to n by 2. So this choice of I equal to n by 2 will create what is called a tree whose maximum height is minimized, and such trees are called balanced binary search trees. Therefore, we will see that we will optimize it when we choose the middle point, and that itself, this choosing I equal to n by 2 will also optimize this recurrence equation. If you look at this recurrence equation and this recurrence tree, this will get optimized. So this is how we develop from this, we develop what is called the algorithm, the very famous algorithm. It is called the binary search algorithm. Now this binary search algorithm tells us that the problem can be solved optimally by binary search following the recursion equation Tn is equal to Tn is equal to, we break it up into 2 equal parts and we have to see only one of them. So Tn by 2 plus order 1. Now somebody could have asked us that we could, so this complexity leads to order of log n, which is the height of the balanced recursion tree in the worst case. We could have found the solution at any earlier point, but in the worst case it will go right down to the base of the tree. And we could also see that our other options were split if we don't split exactly in the middle, and suppose we do Tn is equal to T of 1/3 n or T of 2/3 n plus order 1, we will still get order log n in the worst case. If we do max of these two, the max of these two is obviously the 2/3, so which will be T of 2 by 3n plus order 1. And if we do this, we will still get order log n, but as we have done in a more detailed analysis, this equation of splitting in the middle will always yield us with a much better solution. The third option is we could have split Tn into 3 parts. And done 2 comparisons, and we would have got Tn is equal to Tn by 3 plus 2, and we can show that. And how does it compare with Tn is equal to Tn by 2 plus 1? This is 2 comparisons if we break it up into 3 parts, we have to make 2 comparisons to decide which 1/3 to go into. We can show that this is equivalent to this, where we break it up into 2/3 and 1/3 and again break it up into half or something like that. All of them will yield order of the same complexity, but as we can see, if we want to go even exact into the details, then the breaking up in exactly the middle will be yielding us the minimum. And we can now use the array, and we all know what is the standard binary search algorithm. But the other variations are interesting and important. So let us look at other variations. The first variation is search ordered LS. Like we said before, we have to search for many elements S in L, and how do we do that efficiently? The second is dynamic search, where here L is ordered, but S could be ordered or unordered. I'll leave it for discussion in the class about how we are going to do S and N. Secondly is that we get interleaved queries. That means we get queries where L, so we have got L partially developed. We have operations like insert and find. So we will get several insert operations into L. So this insert is insert into L, and this is find in L. So we will get several insert operations and we will get several find operations. We could also get insert, delete and find. And how do we solve these problems of searching in ordered and unordered lists? In order to solve these problems, we will have to come back to that data structure of how the search tree is formed. And these data structure of how the search tree is formed will yield us to the optimal algorithms of binary search trees. And we shall discuss these binary search trees in more details when we analyze in the class. So I will request you not only to look at the searching of the unordered lists, but to also look at this variant of the problem which we want to discuss in the class, and not only look at binary search and our optimal split, which is a trivial problem all of us know how to solve, but to come back and look at the variants of the problem where we have to search an ordered list for a set S of unordered elements initially and then a set of ordered elements. And then we will find out how we solve these problems in more details. With this, we come back to our methodology, and we are discussing divide and conquer, and we have just started with the simplest of searching problems, and from these searching problems and its variants, we will come to some of the unique not only algorithms but also some of the important data structures that yield the finalization of the algorithm. So I request you to go through these and analyze the variants that we have discussed, which we shall discuss in the class again in more details. Thank you very much. Any questions? We will answer.